Okay, welcome. So what we're going to be doing today, we're going to be going over some rules of circuit analysis. So I'll go ahead and share the notes. And from here, we'll just jump into our circuit analysis. Okay, so first thing I want to talk about is in arrangements of components. Now, the two main terms that you will need to be able to identify are series and parallel. Now, I want to give you a quick definition of what this means. And in order to do this, I'm going to have to define another term. Terminal. Now, what I mean by a terminal is I mean either an input or output of a circuit component. And the way you can think about that is that current will flow into the input and it will um flow out of the output. Now, once you get into more complicated circuits, this more complicated components like transistors, this becomes a little bit more nebulous because those are really three terminal devices, but really what we're going to be dealing with is two terminal devices. And so basically what you'll have for every circuit device, you have a wire going in and a wire coming out. Now that wire might immediately branch, but when it comes to the component itself, you only have two terminals on these devices. Okay. So basically, it's either the input or the output. All right. Now, in order to do this, I'm gonna define series and parallel in terms of terminals. And for series, it's that we'll just put it this way. The terminal, and we'll draw a diagram. Terminal of one device is directly connected to a single terminal of the other. And this is import of another. And the next part is important and nothing else. Okay. If it's connected to something else, then they're not in series. They might not be in anything at that point. But for example, just for a couple of examples, resistors in series looks like the following. So you have a wire going into one resistor, and then that connects directly to another one. Okay, so this is the idea that you have when you have things in series. Now, we put not in series over here. An example of resistors not in series would be you have something like this, and then it looks kind of like it connects to another one, but you have this other branch that connects to something else. Now, those are not in series. Because even though this first terminal does connect directly to the second one, it also connects directly to another resistor. And this could be another component. So we could do something like this and then connect to a capacitor instead of a resistor. Resistors are the squiggly lines, capacitors are the two lines together representing the two plates. So that would be not in series. If we wanted to have capacitors in series, would look like this. So you've got your first capacitor and then directly connected to another capacitor. Okay. I was going to do a third one, but no big deal. So that is what we're talking about when we're talking about series rules. Now, I'm not going to do much circuit analysis with capacitors just so you can see it. Our circuit analysis is basically going to limit ourselves to batteries, resistors, or voltage sources. Doesn't necessarily need to be a battery, but some kind of voltage source and a resistor. Okay. So next thing I want to talk about is parallel. And for parallel, what we have here is that the two terminals of one device are directly connected to two terminals of another. All right. Now, what we have here is so resistors, like I said, we'll do resistors in parallel. And basically what you'd have is you'd have something coming over from the circuit, and then you'd have it go something like this. Okay. And the point here is that basically the bottom terminal, I wanted to change the color. It's going to let me. The bottom terminal, two terminals are connected to one another, and the top two terminals are connected to one another. Okay. They're connected by a wire, by a conductor. That basically means that they're on the same potential. Okay. And that's one of the rules of circuit analysis that we'll get to in just a second. But basically that's what's going on. Okay. So that's resistors in parallel. Now I also want to give you an example. This one messes people up sometimes. This is an example of not in parallel. What you would have is you have something that kind of starts off looking similar, but then on the right branch, instead you would have two. And now the problem is that if you look at this one, like even though it's got a similar arrangement, the idea is that none of these resistors are in parallel because none of the terminals are connected. Okay. Well, the terminals are connected, but the top and bottom of this one is not connected to the top and bottom of another one, so they're not in parallel. Now, how this one would work, maybe you can tell these two are actually in series, not in parallel. Now we'll get into how they can be combined, but that's the basic idea. So combining resistors in series. Basically the resistances, so we'll put it this way: two resistors in series I should include that. In series, add directly to form what we call an equivalent resistance. Equal to the sum of the two independent resistances. Okay, so the idea here is that if we have something like this in our circuit diagram, it's like R1, and then it's connected to another circuit. This is R2. Basically, this can be rewritten. You can redraw a new circuit diagram as just a single resistor, where this is R equivalent, and R equivalent, I'll put it down below and bigger, R equivalent equals R1 plus R2. Okay. And this is a lot of times our method for simplifying circuits. We go around and we'll combine circuits if they're in series or in parallel. We'll get to the rule for parallel in just a moment. But we'll combine them and redraw the diagram in a simplified fashion. A lot of times doing that can make the circuit then easier to analyze. Now, it's not the entire story of it, but this is something that happens. Now, the idea here is the reason for this is that You might not know what the voltage drop across these two individual resistors are, but you might be able to tell the voltage drop across the entire thing. So for example, the idea here is if you have something like this, where you have, by the way, this is a voltage source. We'll get into a minute, voltage source. And you have something like this, and then something like this. The issue is that without a voltmeter, you don't know, call this V, R1, R2. Without a voltmeter, you don't know what the voltage drop across R1 and R2 is. So we don't know, so we'll call that V sub S. We don't know, can't write. We don't know V1, that's the voltage drop across R1. And we don't know V2, which is across R2. But what we do know is we do know that that ultimately, and we'll get into why this is the case, we can figure out the drop across our equivalent. Okay. And this is the idea. If we can combine those into our equivalent, we can use some of our other circuits resources, and then we could use Ohm's law. So if we knew the voltage, across our equivalent, we could use Ohm's law to find the current, and then we know a lot more about the circuit at that point. Okay, so that's why this might be useful. Now we'll talk about combining resistors in parallel as well. And the idea here is that, again, so we'll give you so two resistors in parallel combine to form an equivalent resistance that is the reciprocal of the sum that is the reciprocal sum of the two independent resistances. All right. Okay, and basically what I'm saying here is I'm saying we have something like this, R1, R2. And the idea here is that these can be combined into a single resistor, which is just R equivalent. Okay. Another thing I've noticed in the past, some people they get a little bit worried when you have wires start bending. This doesn't mean anything. A lot of times you'll go have your wire go at a right angle just to make the circuit a little bit more clear, a little bit easier to read. But again, like we could just easily make this thing horizontal. It doesn't matter. Like it's not about the array. It's not about how the circuits are situated in the diagram. It's about what they're connected to. Okay. And the idea is that for this formula, what we get is that 1 over the equivalent is equal to 1 over R1 plus 1 over R2. A lot of times you'll see this written as the following: R equivalent equals, and in parentheses, 1 over R1 plus 1 over R2 to the negative 1. That is another way you might see this. But either one of these equations is going to be your rule for how things add reciprocally. Now I'll go through we'll once we do the conservation laws in in circuits, we'll go through where these things come from, just a quick little analysis to go to kind of understand where these things will ultimately come from, and then we'll go from there. Really, these things can be verified experimentally, but they can also be proven from the conservation laws that apply in circuits. But before we do that, I want to talk about this concept that comes up in circuits. It's electromotive force. And really what we mean by electromotive force, if you take away one thing, think of it as a voltage in a circuit. Now, I was always curious, why didn't they just call it a voltage? Okay. The idea is that electromotive force can come from a number of different things. It can come from an external voltage applied, so from like a power supply, but it can also come from a battery. Now, in this case, the difference is that voltage is more of an electrostatic concept that has to do with the potential work that electric fields might do. And there's a certain way that you conceptualize that's what's going on in the circuit. It's a little bit difficult to think of it that way, which is why people came up with this idea of electromotive force. Basically, in the case of a battery, what you're doing is you're using a chemical reaction to ultimately drive current flow. Now, that's a little bit different. And again, you can all these things can be resolved when you analyze them at a fine enough level, but using a chemical reaction to drive current flow is a little bit different than using an electric field to drive current flow, if that makes sense. So that's where this idea of electromotive force comes from. Excuse me. You can also have an electromotive force from an electrical generator. Actually, we'll talk about this. We'll talk about this later, but we'll talk about this in the next lecture. You can also have an electromotive force from what we call a change in magnetic flux. I don't want to get into that now because that's a little beyond the scope. I'll talk briefly about that in the one lecture I'm going to give on magnetism. But basically the idea is an electromotive force generates a voltage, okay? And you can think about a voltage as ultimately voltage is, you need a voltage in a voltage source in a circuit to drive a current, okay? So the idea here is that the symbol that we will use in general will just be one longer line, one shorter line. And your terminals actually have a plus and a minus on them. And a lot of times you'll just label it. Sometimes you'll label it V, or occasionally you'll see this weird cursive E. I don't really like that. I really prefer V. So that's how you'll see me do it in my diagrams. But basically what you're saying in this one is that you're saying that, on the plus side, this is higher voltage. The minus side is lower voltage. Now, another thing that you will occasionally see in circuits is another idea that I want to talk about, and that is this symbol. It's 3 lines, each one getting smaller. It's a little bit different, but what this means ground. And what ground implies is that your voltage at that point is 0. Now, a lot of circuits, they don't necessarily rely on there being ground, at least not theoretically. In practice, they do. You really want to have in general, what you want, this isn't always true, but you want to have some kind of ground. If it's a DC circuit, you kind of prefer to have your lowest voltage be ground. It doesn't need to be that way. It's just always how I've seen it done. But the idea is like basically this is your reference point, okay? And what you don't want is you don't want a floating reference point for various reasons. That has to do with what can happen if you try and operate a circuit that's not grounded. You can have sudden discharges, which can be a problem. You can have a buildup of static charge in the circuit, and a sudden discharge can actually damage the circuit. So this is why we tend to have grounds. Again, not all circuits have them, but that's the symbol. That's what that means. It just means that anything that's connected to that symbol automatically has a voltage of 0. Okay. And you change voltages. Basically, so the idea here, the reason I brought this up is that let's say, we'll just do an example. Let's say we have a partial circuit, and this isn't a complete circuit. It needs a loop to do this, to be a complete circuit. Let's say you have a partial circuit and it's connected like so. Now, basically what this is saying right here, I'll do my analysis in green. This is saying that on this wire, you have a voltage of 0. Now, on the wire above, let's say this is plus minus and V equals 5 volts. What it's saying here is that on this wire up here, you have a voltage equal to 5 volts. Now, the idea then, if we continue this circuit and we just have a single resistor, and I'll say R equals 50 ohms. The idea here is that what we know now is we know that up here is 5 volts, down here is 0 volts. So the voltage across the resistor equals 5 volts. Now, what does that mean? Well, it means we can now find the current across the resistor. So VR equals I times R. We know R and VR. So we know that that R is then going to be equal to VR over I. That's from Ohm's law. And that's just going to, sorry, what I want to do. I is equal to, because we want to solve for I is equal to VR over R, which will be 5 over 50, which will be 0.1 amps. That is 100 milliamps. Okay. So that is how, that's a very simple sort of little analysis with that circuit. Now, one thing I want to mention here, this is something that some people it's kind of a little shortcut when doing circuit analysis. It's that voltage is constant on wires in the circuit. Now, this is a little bit of an oversimplification, but for the most part, in the context of the small circuits we're going to be using, we're going to assume the wires have 0 resistance, which means that there is no voltage drop. If 0 resistance, no matter what the current is flowing through the wire, you don't get any voltage drop when you flow through the wire. Basically, what this means is the wires aren't dissipating energy. Now, again, that's not quite right, but that is fundamentally how we're looking at it. Okay. So that is, those are some symbols and quick analysis pieces. One thing I wanted to look at, or next thing I wanted to talk about, the conservation laws in circuits. And the conservation laws lead to what we call Kirchhoff's laws. And these are two of the, for those of you that have taken circuits before, you probably know that these are two of the most important tools for analysis in circuits, and ultimately they come from the conservation of various quantities in circuits. So the first one I wanted to talk about was conservation of charge. And what this is saying is that charge is neither created nor destroyed. Now, fundamentally, what this means, if you recall, one of the ways we got to the continuity equation in fluids was we said that was conservation of mass. Because mass wasn't created or destroyed, any water flowing into one point had to be flowing out of, you had to have the same amount of water flowing out of that point, is the idea, or really a cross-sectional area. Now, similar sort of logic is going to apply here, except this time it's current, okay? And the idea is that current into a point must equal current out of a point. Because if it didn't, that would mean that some amount of charge was either created or destroyed, which would violate conservation of charge. So the idea here is that in simplest forms is that if we had I1 and then over here, I'll do this in green, we had I2. Well, what this is saying, what conservation of charge is saying, is that I1 has to be equal to I2. And the idea is that if we view this as our point, Well, I1 is flowing into that point. I2 is flowing out of that point. The only way for that to work is if I1 is equal to I2. Now, this is not Kirchhoff's law. Kirchhoff's law applies to junctions. So it's sometimes called the junction rule or the current rule. And in this case, what is going on is that if you have something like this, where you have where you have a circuit that branches, okay? Now the idea is that if you will have I1 and then I2 and then I3, the idea here is that if we analyze this point, what goes into that point is I1. What goes out of that point is I3, but I2 also goes out of that point. So it's I3 plus I2 or I2 plus I3. Now, the idea is that in I sub in should equal to I sub out. Okay. So basically, what this is saying is it's saying that I1 is equal to I2 plus I3 for that circuit that I have drawn. Okay. And if you have more branches, then you have to you have to take those into account. May have current flowing in, they may have current flowing out. Now, one of the problems that people have with this is a lot of times you're asked to solve for currents. Sometimes you're given it, but given that we can reliably apply external voltages, it's a little more difficult to reliably apply external currents. A lot of times you end up needing to do circuit analysis to solve for the current. And one of the problems that people will have sometimes is that excuse me, is that they don't know which direction the current is going to flow. Sometimes it's clear, sometimes it's not. Now, my advice is don't worry about that. If you end up drawing draw the direction you think the current's going to flow. If it turns out you're wrong and you do your circuit analysis correctly, you'll find that your current is negative. All a negative current means is it means you drew your arrow in the wrong direction. Okay. So the idea is, well, what if, I2 was actually flowing into the junction instead of out of it? Well, then this equation would be a little bit wrong. But the point is that I2 would end up being negative once we found that in the original setup. And we could, we could ultimately just move that over to the other side and we'd have the right equation. Okay. So that's the idea, is that you get a slightly different equation. In that case, you would get I1 plus I2 is equal to I3. But again, it's not a huge deal when you think about which direction the current, or it's not imperative that you get the direction right, because eventually when you do your analysis, your numbers will work out and tell you if you picked right or not. So that's the idea. Okay, so this is the main junction or current rule. Now, the rule for parallel circuits comes from this parallel resistors, we'll say. The rule for parallel resistors comes from this idea. So the idea here is if we have parallel resistors, we have R1 and R2. There's a couple of things that we know, and I'll do this in red. So I'll do voltages in red. So we'll call that V1 and we'll call that V2. And we actually know that V1 equals V2. And the reason we know that is because the top terminals are connected. So those are the same voltages. And the bottom terminals are connected. So those are the same voltages. So basically what we mean by V1, this is the voltage drop across R1. And what we mean by V2, this is the voltage drop across R2. And the idea is that because those you have the same voltage on the top as you do on the bottom, the voltage drops are going to be the same. All right. Now, here is the thing. What about, let's say we just have I1, we'll just do this like we did before, and then we have I2 and I3. Now, again, you got to remember that because this is just a straight shot, I3 is going to go from the junction all the way down. Now, the idea here is that Kirchhoff's current law gives us I1 equals I2 plus I3. Well, the idea then from that is that, okay, this is fine. What we can do now is we can look at these different voltages. Sorry. Actually, I'm going to change these just to match. So I'll call that I2, I1, and I0. Okay. So just to match the resistor number. So I0, I1, I2. All right. And now what we have is we have, okay, V1 equals I1 R1. V2 equals I2 R2. But V1 equals V2, and I'm just going to call that V. Okay. So what we get here is we get, all right, so V is equal to I1 R1, but it's also equal to I2 R2. Okay. Now, the idea here is what we want is we want some R equivalent where R equivalent will be equal to our, well, put it this way. Voltage will be equal to our total current, I total, times R equivalent. Okay. Now, how are we going to do that? Well, I total is just going to be I0 because that's equal to I1 plus I2. Okay. And again, like the basically the way you should think about is like I0 got split into I1 and I2. All right. So the idea here is that, okay, what we have is we have V is equal to I0 times R equivalent, which is also equal to I1 R1, which is also equal to I2 R2. Well, how are we going to resolve this and solve for I equivalent? Well, or R equivalent, I should say. Well, what we can do is we can say, okay, what is the best way to go about doing this? Oh, I don't know if I can quite do it yet. No, I think I can. All right. Yeah, I think I know what I want to do. What I'm going to do is I'm going to, I don't know. I don't remember if I need the another law or not. It's easier with another law, but I think I can do it with this one alone. Okay, yeah, I remember how to do it now. Okay, so what we could do is we could say, okay, I0 is equal to V over R equivalent. I1 is equal to V over R1. And I2 is equal to V over R2. Now, last thing we need to do is we need to remember that I0 is equal to I1 plus I2. And then what we can do is we can do all of these substitutions into here. So we get V over R equivalent, that was just I0, is equal to V over R1 plus V over R2. And the idea is that we can factor out a V on the left side, well, on both sides, really. So we have V times 1 over our equivalent is equal to V times 1 over R1 plus 1 over R2. And the V's then cancel. And this, as a reminder, is just what we got as our combination in series rule right there. Okay. So another thing to take away from this analysis real quick is that voltages across components in series are the same. Okay. So that is an important thing to remember, is that if you have two components in series, they will have the same voltage drop across them. All right. So the last conservation rule I want to get into is the conservation of energy. And the idea behind conservation of energy is that a charge cannot gain or lose energy in a trip around the circuit. In a trip through a circuit, let me put it this way. So the point is that in order for current to flow, basically what has to happen is you have to have a path so charges can constantly move through the circuit. And the idea is that no charge can gain more energy than it loses or lose more energy than it gains. Okay. So just for an example, simple circuit, we have a voltage source, V, and we have a resistor, like so. And we know that it's actually electrons, but I'm just going to say what we have is we have a positive charge right at the top of this EMF source, this voltage source, and this charge goes along. It's doing this basically because the voltage is pushing it to do that, and there's no real resistance when moving through a wire. But when it encounters this resistor, well, what you have here is you have, in order to get pushed through the resistor, the charge loses energy here. Now, basically, then it gets to the bottom, and ultimately, the charge still gets, it still gets pushed, but then the charge will gain energy from the EMF. Okay, so charge gains energy from the voltage source, whatever that happens to be. And the idea is that the energy gain has to be equal to the energy lost for that charge. Well, the idea is that if we kind of remember, the whole point of using voltages was to abstract away from a charge moving actually around the circuit. What this implies is that the voltage gain, and this is really from EMFs, has to equal the voltage loss or drop. And this is generally from dissipation in the case of a resistor, but it could be from storage in the case of a capacitor. Now, again, we're not going to get into capacitors, but you can drop in voltage because you've decided to store charge. And the very act of storing charge causes a voltage drop across that capacitor, okay? So you think about EMFs, those voltage sources, as being voltage gains, have to be equal to voltage losses. Now, what this means, this is Kirchhoff's loop rule, or voltage rule. Kirchhoff's voltage rule, or loop rule. And the idea behind this is that any voltage gains in a closed loop, and the loop has to be closed, okay? So I will underline that. No current will flow through a non-closed loop, so there's not really point in analyzing the circuit. Like in a well, it's not a loop if it's not closed, but like if you had a circuit that was open, that wasn't a closed loop, you would get no current flowing, and you could, in principle, just gain in voltage, but not have any current flow. Okay, so that this only works for closed loop. Must be offset by voltage losses. Okay. So the idea here is that, again, in this example, and this will be true for any. So we have plus minus, this will be our source, and then we have plus minus, this will be the voltage across our resistor. The idea here is, I'll just draw a path, and I'll do it, is that clockwise? The idea is that, okay, so we start here and we'll figure out the voltage drops and gains. If we go from minus to positive, that is a voltage gain, okay? And this is when we're doing it in a loop. So that means we have a plus V sub source. So any charge we had going starting from this point, first it would gain a voltage source. Now it doesn't do anything on the in the wire, but when we get a voltage drop, so then we would have a minus V sub R, and then get down, go to here, we get back to where we started. Once we get back to where we started, we sum up our voltage gains and our voltage drops, and they should be equal to 0. Now what this gives us is it gives us that our voltage source is equal, the voltage of our source is equal to the voltage across a resistor. And this is where the idea that sources of voltage, or that objects in parallel must have the same voltage, because if they're in parallel, you can do a closed loop between them, and you're only going to get one voltage drop and one voltage gain, and those two have to be equal to one another. Now, the idea here is that this can help us to kind of analyze the series rule if we do this correctly. Now, first thing to know, so we'll just do a quick little circuit. So we have R1, R2, and it goes like this. Now we'll have a voltage of a source. Now, the whole point of this is we would have, I'll try and color code things differently. We would have I1, I2, and then we would have plus minus V1 and plus minus V2. Now, the idea is we don't know what V1 and V2 are in this case. However, what we can say is we can do a little loop like so. Okay, and if we do that little loop, what we know is that V source, that's what we gain. We subtract V1, because we then come to the resistor 1. We subtract V2, those, and then we will come back and get to where we started. Those should be equal to 0, which means that our source voltage has to be equal to V1 plus V2. Now, we also know here that I1 has to be equal to I2. This is just Kirchhoff's current law, and basically because there are no junctions, you're only going to ever have one current flowing through this circuit. So this is just going to be, I'll just call that I. And the idea here is that I1 R1 equals V1, I1 R2 equals V2. That's just Ohm's law applied to both resistors. And so that means I R1 is equal to V1. That's only 2, but I R2 is equal to V2. And then what we can do is we can just plug these things in to what we were saying. Now, the last thing I want to talk about is we should be able to say that our V source is just equal to I times whatever equivalent resistance. Basically, we want to boil this thing down to just a single resistor, okay? And then we're going to make all these substitutions into there, okay? So we get I R equivalent, that's for our V source, is equal to I R1, that's V1, plus I R2. Well, notice, just like the voltage canceled out in the previous one, the currents cancel out here. So we have I, R equivalent, is equal to I times R1 plus R2. The I's will cancel, and we just end up with R equivalent is equal to R1 plus R2. Okay, so that is where that series rule comes from. Okay, so by using these principles of conservation of charge and conservation of energy, you can derive both the parallel rule and the series rule. I do want to do one example problem just to show you sort of a little bit more detail how you would go about analyzing this. So, and how you can use these rules. So I'm going to do that. So here's our example circuit right here. Now, what we have here is we have two, and like I say, you like the cursive E, we have two voltage sources, kind of like so. We have R1, little R1, that's actually an internal resistance to the batteries. We didn't really talk about this, but most EMF sources have some sort of internal resistance to them. And basically what you do is you draw a resistor in series with the positive terminal of the battery. Okay. So here's how I would go about doing this one. Now, you can do this a number of different ways, but one of the things that happens here, the first thing I would do is I would look at the junctions right here. And they've already drawn the current arrows. You could do that as well. Now, so first thing I'll do is I'll apply the junction rules. And we see this junction right here. So we'll call this 1. And into that, I've got I2 plus I3. These are both my ins, and that should be equal to my out, which is I1. Now we could do another junction at A, but we'd actually get the same thing. It's just I1 is in and I2 and I3 are out, so it's the same exact equation. Now what I'm going to do is I'm going to do my loops, and I'm going to do this in a different color. So this is loop 1, and this is loop 2. Now, I don't know that that's going to be enough. I'll do loop 2 we'll do loop 2 in a different color. But for loop 1, we'll just show what I'm going to do. Now I'm going to start at A, and I'm going to give all my voltage sources. Now, this is another place I want to indicate to be careful. A lot of people, they look at this and they're not sure, okay, is that a voltage gain or a drop across that resistor? Well, here, check this out. Whichever side the current is flowing into, put a plus and then a minus on all your resistors. So I'm just going to do that here. So we have a plus and a minus there. And again, I3 is connecting, so a plus and a minus there. Now, the reason that this will work is that if you go from positive to negative, that is a minus, okay? So that's minus, and I'm just going to write this. I'm going to do a shorthand and do Ohm's law. So instead of V2, I'm just going to write I2 R2, because that's just what that voltage is. And then I go from a minus to a plus, so that's going to be plus EMF1. I'll just call that V1. So that's the V source one, which is 18 volts. And then we have, again, we go from minus to plus, so that's another subtraction. So that's minus, and again, it's I2, but this time it's little r1. Okay? And then we continue along this curve, we get to here, and then that would be minus I1 R1. Okay, so that would be loop 1. All right, now loop 2. I'll start at let's do loop 2 in a different color. Do it in purple. I'm going to do it like this, and you'll see something that's a little bit different. So I'll start here, and I go up, 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 and the first thing I get to is this resistor. But this time, I'm going the wrong way, okay? Now, I could have done the loop in the other direction, but I want to show you how to do the signs, which is why I'm going the wrong way. But the thing is, this is why I drew the terminals. If as I'm going around my loop, I go from minus to positive, I can just make that positive. So that's just I1 R1 right there. And then as I go from as I continue going around, I again go from minus to positive. So that would be plus I3 R3. And then I go, okay, minus, or no, it's plus again because I go from minus to positive. So it's plus I3 R2. And then because I go from plus to minus here, that is going to be a minus 45. Now, the first thing I forgot in the zero or in the first equation was that these should be zero. Now, we in fact know all the resistances. We just don't know the currents. So basically, the idea is that now we need to go ahead and find the currents. So I'm going to rewrite these three equations with things that we know. So what I've got here is I've got I1 equals I2 plus I3. And then I'll rewrite everything as positive. So I know V1 was equal to 18. And then I'll remove all the negatives over there. So R2 I2, that would be 2.5 I2. I2 little R1, that would be plus 0.5 I2. And then it would be minus, or no, plus 6 R1, because R1, or 6 I1, because R1 was equal to 6. Okay. Now we can actually do some combinations here. And the thing is ultimately, because both of these are multiplied by I2, we can combine them. So that's just 3 I2 plus 6 I1. Okay. Now setting up loop 2, the reason so this was loop 1 right here. And then loop 2. What we have here is we have 45 is equal to 6 I1 plus 1.5 I3 plus 0.5 I3. So this is just 45 is equal to 6 I1 plus 2 I3. Now, what I would go ahead and do here is I would probably go ahead and substitute in for I1 into both of these equations. So again, redoing loop 1, this time making the substitution, that's 18 equals 3 I2 plus 6 times I2 plus I3. Okay, so rearranging this a little bit, that would be 18 equals 9 I2 plus 6 I3. All right, now loop 2, doing the same thing. So that's 45 equals 6 times I2 plus I3 plus 2 I3. All right. Now what we have here, splitting that out, 45 is equal to 6 I2 plus 8 I3. And now we can do a little bit of reducing, but these are the two equations we want to solve, and these are our two algebraic equations. So this one will actually become, I'm going to divide everything by 3. So this will be 6 equals 3 I2 plus 2 I3. And then we'll have 45. So then we'll have 45 equals 6 I2. I think I can't divide everything by 2 there. So I'm going to leave that, plus 8 I3. Now what I'm going to do is I'm going to multiply this by 2. So that's going to be 12 equals 6 I2 plus 4 I3. And now what we can do is we can subtract this equation from this one. So that would be a minus 12 minus 6 I2 minus 4 I3. And those cancel. We should end up with, what is that? It's going to be 33 equals 4i3. And I think that I3 is going to end up being, we divide that, it'd be like 8.3 amps, I believe. Okay, so that'd be 8.3 amps for I3. Now we can go back and we can find I2. Is that right? Seems a little off. Okay. Just gonna verify this. So yeah, I rounded, but yeah, it would have been 8.25 amps, not 8.3 amps. So I'll leave it there. Okay, so now what we would do is I'm going to go back and I'm going to use this to find I2. So we have 6 equals 3I2 plus 2 times 8.25. It's going to give us 6 equals 3I2. And then 2 times 8.25 will be 16.5 plus 16.5. And when we divide or subtract this, subtract minus 16.5, we're going to get negative minus 16.5. We're going to get negative 10.5 equals 3. I2. I2 is actually going to be negative 3.5 amps. Now, the whole idea behind this negative is that means I2 was drawn in the wrong direction. Okay? And this is why I say it doesn't matter. So we go back up to this circuit diagram. I2 was drawn as going from the positive terminal or the negative terminal to the positive terminal, which you would not, that's not a bad idea, but it turns out that's incorrect. Current is actually going to be flowing the other way across that battery. And it turns out that by doing this, by forcing current to flow the wrong way across the battery, this is a lot of times how, if the electrical or the chemical reaction can be done in reverse, this is how it's done. You force current to flow the wrong way, and you can undo the chemical reaction is the idea. So I2 was just drawn in the wrong direction. We should probably find I1. That one's easy. I1 was just equal to I3 plus I2, which would be 8.25 minus 3.5. So that would be 5.25 minus point, and that would be 4.75 amps for I1. Okay, so that is how you would do this. I don't think I will give anything this complicated when it comes to circuits analysis. Like I say, we don't have a lot of time to go over this, and I don't want to. Like for some people, this is going to be a bunch of review. For others, it's going to be completely new. I don't really want to spend a ton of time on this topic. But this is the basic approach. Like I say, nothing will be sort of this much, but basically this is the strategy that you're going to want to take when doing these problems. Okay, so with that, I'm going to go ahead and end this lecture.